Uh, okay, ladies and gentlemen, welcome back to the Mali seminar. So it's our pleasure to have Chris Phillips from University of Oregon. And Chris is going to talk about mean dimension and the radius of comparison of the cross products. So, okay, Chris, take it away.
Yes, okay, thank you. Thanks for the invitation to speak here. So this is joint work with Elon Hirschberg. And I gather he talked here either in this one or maybe in the other one a couple of weeks ago about the same thing. So I will take a somewhat different approach. I will say a little bit more about proofs and so on. There will be some overlap, but I'll give what I've prepared here is a fair amount of sort of background to explain really what the pieces are, and then give an indication of how they fit together, because the pieces are a bit unconventional. On the other hand, some of it people have seen. Let's see. Let me just check. How much should I say about Kunz comparison? Only barely heard of it. Okay, so yes. Okay, so I actually prepared a certain amount about Kunz comparison. So there are two main ingredients here. One is mean dimension, and one is Kunz comparison. And I'm going to try to say what Kunz comparison means and how it's related to dimensions in general. And then I will talk about mean dimension later. And since Elon defined that, I'll be a little bit somewhat sketchier about that. Okay, so here's a C-star algebra. And we take A and B in, well, I'll take the M infinity of A. So this is equal to so a positive part here. This is the union for n equals 1 to infinity of Mn of A with embeddings like this. Well, let's see here. This. So here is A. Here is M2 of A, etc. So you put A in the upper left corner and so on. Then A is Kunz subequivalent to B if for all epsilon bigger than 0, there exists a V in M infinity of A such that norm of VB, I guess I put the star here usually, B star BV minus A is less than epsilon. Okay, so notice that if you're doing Murray-Van Orman subequivalence of projections, you get, well, the notation is, of course, conventional notation is different, but I'll stick with this. You get B star BV equals A. You do not get that here. And so here is an example of what it does in C of X. So I'm really just sticking inside not matrices over C of X, but just C of X here. Let's say I still call them A and B. A is Kunz subequivalent to B if the open support of A is contained in the open support of B. And what is this? This is a set of places X, A of X is not 0. You can't call this support because it has already a standard meaning, which is the closure of this set. So here is a picture. Let's say X is 0, 1. And this thing here is A. And this here is B. So then A is Kunz subequivalent to B, but there is no V such that V star BV equals A, right? You get in trouble here. It would have to be unbounded. So that's the reason for this more complicated version. What it does is something more or less like, well, since one doesn't make the the Grothendieck group, it's really like the Merva-Norman semigroup, the ingredient which goes into making K-theory. But because of this, the basic lemmas, there's about 4 times as many of them. And everything is much more complicated. Okay, so in the n by matrices of the complex numbers, A is equivalent to B if and only if the rank of A is less or equal to the rank of B. Should be at least naively plausible. Okay. So the analog of this in C of X Mn is not true. You might hope if you had a pointwise rank inequality, you would get cone semi-equivalence, and you don't. And this already goes wrong with projections. So I'll be talking a certain amount of projections where things are easier because I really actually can do this. So recall. So we'll go into this. So recall that a projection corresponds to a vector bundle Okay, should I say something about what vector bundles are? Are people familiar enough with them that I can just use them? Yeah, okay. Whose sections, say, let's say E, whose section space is the range of P with P regarded as an operator Mn of C of X, thought of as, well, it's as the collection of really C of X linear maps from C of X to the N to C of X to the N. Right, this is I'm taking it to be a right C of X module, and so I'm looking at C of X module homomorphisms. And the fiber P of X is the range of P of X. So just to put that properly in context. Okay. And so then a trivial vector bundle corresponds to a projection which is Murray-Van Norm equivalent to a constant projection. And I'm going to call these projections in this talk, I will call them trivial. This isn't standard terminology and probably should not be used in any formal way, but at least not without explanation. But that's what's convenient here. Okay. What's the simplest example you know of a non-trivial vector bundle? Okay, so that's a fiber bundle. Oh, the vector bundle which comes from. Okay, so yeah. Yeah, so there's one which I can draw, but it's over the real numbers rather than the complex numbers. The Möbius strip. So the real case, this is the only non-trivial bundle I can draw. Here is X. And the fibers, well, let me start here. So each of these things associate a copy of the reals, but sort of condensed into the length of an open interval, say from -1 to 1. They're homeomorphic, so you can transplant the vector space structure. And so when you try to make a non-zero section, you start, let's say, here. And you go around like this. Whoops, I did this wrong. What's wrong with this? Yeah. So I come back. Yeah, it's right. So I come back here instead of up there. And so again, I can give you a real version of failure of. Oh, okay, so you would naively hope that if the dimension of Ex is less than or equal to the dimension of Fx for all x, then E is isomorphic to a subbundle of F, or less than anyway. This is not true. And essentially how well you can do depends on the dimension of the underlying space. And again, there's an example which is easy to give, but also over the reals. So I will take X to be an even sphere. And I will take the real vector bundle is just the tangent space. This vector bundle has rank 2n. And you look at one-dimensional trivial bundle. R cross X. This is not a subbundle of this. So it's rank 1. Okay, so why not? Well, suppose it were, then you would have a never vanishing vector field on S2n. And it's a standard theorem in differential geometry. There's no such thing. If you had one, for example, then you could follow the corresponding differential equation for distance epsilon and get a diffeomorphism of S2n, which has no fixed points. And this contradicts the Lefschetz fixed point theorem in algebraic topology. That's the proof I actually know, although I don't think that's the original proof. Probably just goes back to the what is it? The Brouwer fixed point theorem. Okay. All right, so now I'm going to go back to the complex situation. Theorem. This is to be known for a long time, at least for finite complexes, and you get to general cases by taking inverse limits. And let me to keep things simple, I'll assume X is connected. This means that the fibers all have the same dimension. So if E and F are vector bundles, are complex vector bundles, or X, and if the rank of E, just the dimension of one of its fibers, plus 1/2 of dimension of X minus 1 is less or equal to the rank of F. And this is covering dimension. And I will say more about that later. Then E is isomorphic to a subbundle of F. Okay, so now you might hope to detect the dimension of X this way, but you do not. So example, Hilbert cube. Is infinite dimension. It's contractible, so all the bundles are trivial. So, okay, I've got to be careful because this thing is obstructing somebody's view. Can it be gotten? Nope, that's not a good idea.
I mean, I actually can see you on the screen anyway.
I see. Okay. Yeah, I'll move the board up eventually anyway, but it is going to be sort of annoying. Maybe I should just not use this board. Started on now. So rank of E less than or equal to rank of F implies E is a subbundle of F. But now, let's suppose, right, I started off defining comparison for positive elements, and here's why. So suppose Y is contained in X, closed, and you have, and here I'm interested in the case Y has complicated topology. And I have in F vector bundles over Y. I take corresponding projections P and Q in C of Y M n for some large n. And then I extend to a neighborhood U of Y. I extend them just as functions and then use by Horizon, and then I use functional calculus on some neighborhood. And so I get, let's say, P tilde and Q tilde. Then choose F such that, so F and C of X such that now, all right. Okay, and I hope everybody has gotten everything off of this that they need. Yes.
How does that theorem relate to the thing just up there? The theorem only applies to complex vector models?
So how does this theorem?
So yeah, 'cause I mean, you just gave an example where, you know, you have a bundle.
Oh, yes. So I'm interested primarily in the complex case. In the real case, I think you get rid of the factor, the 1/2. Maybe slightly off. So, but yes, there are analogous theorems for real vector bundles in which you have roughly the dimension of X here. And also for quaternionic vector bundles in which you have something that's roughly 1/4 the dimension of X here.
So if it was, if you go to the half, then it doesn't apply to the thing just above.
Yeah, but you see, these are real ones, and so I should get rid of the 1/2. And in fact, this is, I mean, the 1/2 comes from the fact that the complex numbers have dimension 2. And this will come back. This is why in the conjecture, there's a factor of 1/2. And if you did the real cross product version, then you should not have that factor. Let's see, I wanted to put this down here. And then, so such that f equals 1 on y and support of f is contained in U, and then I take A equal f times p tilde, which is now defined everywhere, and B equals f times q tilde. And if the extension was done with reasonable care, right, I don't want to say that U contains some other set which is somehow separate from Y, and where I did something crazy with the bundles. Then A is subequivalent to B if and only if P is subequivalent to Q, which is if and only if E is a subbundle of F. And these things are positive elements. So what this means is that using this kind of comparison, rather than restricting oneself to projections, one can actually detect even, for example, the fact that the Hilbert cube is infinite dimensional. The Hilbert cube contains basically every other compact metric space. Compact, yeah. Okay, and so when I wanted to try to capture something or other about, I mean, this is sort of one version of dimension of C-star algebras, competing with real rank, stable rank, nuclear dimension, several other things, and they all behave differently. Let's see. Yes.
Being very slow, just the comment that Tristan was making about this theorem. So if E is the trivial bundle, then it's round 1.
Yes.
The round of the target model is 2n.
Yes.
On the left hand side, you have 1 plus.
Yeah, but this is the real case.
Yeah, I get that.
Yeah.
If you get rid of the half, and then on the left, you have 1 plus 2n minus 1.
Yeah, I didn't check what the exactly correct thing here is. Right, it may be it's dimension. It's something that's roughly half the dimension of X. Or roughly the dimension of X. I don't remember if it's -1 or -2 or whatever. Yeah. Right. I mean, I mean, the real ones are the ones you can see, so that's why I'm using them in the example. But the constants are off. Let's see. The last thing I wrote on was there, and so that's what I want to leave. Okay. So now I want to find a size on for a not necessarily commutative C-star algebra, which corresponds to the rank of the bundle. And I'm going to use traces. But I want to find rank and not just the trace of something or other. And so here's the definition. Let's say T of A is the tracial states of A. And now I'm going to assume A is unital. I also assume A is exact, because if it's not, then you have to worry about quasi-traces, which I don't want to say anything about. And then so now so tau in T of A, so I extend to Mn of A without renormalizing. So that tau, the identity of Mn of A, is n. And this gives me something that's defined on M infinity of A. I'll just use the same letter for it. This is standard. And now for A in M infinity of A, positive part, we will define d tau of A to be, well, I'm not going to take tau of A, I'm going to take the limit as n goes to infinity of tau of A to the 1 over n. I want to note that I get the same thing. So first, I was worried about where the limit exists, which it does. Lambda bigger than 0 implies that d tau of lambda A equals d tau of A. Since lambda to the 1 over n goes to 1. And if norm of A is less than or equal to 1, which I can assume because of this part, then the sequence tau of A to the 1 over n is non-decreasing and bounded by n if A is in Mn of A. So limit exists. And on C of X, is in C of X, tau comes from measure mu. Let's say norm A less than or equal to 1. Then A to the 1 over n is positive part. Converges pointwise, non-decreasing to the characteristic function of the open support of A. And so by the monotone convergence theorem, d tau of A is the measure of the open support of A. If A is in C of X n, and tau is evaluation at X, then d tau of A is the rank as part of your rank of A of X. And you get the rest of them by, well, you integrate, you look at what places where the rank has various values and take measures of those sets and multiply them by ranks and add them up. And so now, definition. A has R comparison. Here R is a real number. I guess I want bigger than 0 here. If, no, bigger than equal to 0 is okay. If, whenever A, B are positive elements in the matrices, and for all tau in T of A, d tau of A plus R. So where R is this, I mean, it plays the role of, where was it? Here. Here's something related to R. Is less than d tau of B. And A is sub-equivalent to B. In that definition, radius of comparison of A is the inf of the set of R such that A has R comparison. If it's simple, then it's just the least R which works there. Otherwise, it's not so clear. And just to connect this with other things, sorry, let's see. Yeah. So part of Thomson conjecture is really the only part where there's still part of it is open. Says RC of A equals 0. This is called strict comparison. And A simple separable unital nuclear. This implies that A has finite nuclear dimension. And so classifiable in sense of the Euler program. And this is known for, this is known for lots of choices of A. Converse is always true. Converse is known in general. Oh, I should say, I forgot the UCT. Converse is known in general. So radius of comparison 0 and suitable hypotheses of non-dimensional type should be equivalent to classifiability. Questions? Yes.
Maybe you didn't want to say too much about this, but can you remind me what the current state of the art is for this direction? Do you need A to be have a Bauer simplex or something?
You need to know the extreme boundary of the tracial state space is compact and has finite covering dimension.
Oh, okay, so it's still that needs.
I'm not aware of any general further results, although I think maybe in some special cases. I think there were some special examples done that aren't in this covered by this, but I don't remember.
Sure. Okay, thanks.
That was like just makes it compact.
Another quick question, if you don't mind.
Yes.
Is it clear that you need the UCT for either of these comparisons? Either of these, well.
For this sort of stuff, no.
Okay.
This has nothing to do with the UCT.
Okay, I didn't.
Well, okay, some of the proofs may have something to do with the UCT. Certainly some of the things about, at least some versions of I'm not sure if you can get the UCT out of the things known for the Thom-Smitter conjecture. You do have to have the UCT for classifiability. And it's still open whether the UCT is automatic for nuclear C-star algebras. Okay. So lower bounds are RC of C of X. I should put up the result first, but then I want to say, give some indication of what goes into the proof. So this is a result of, I wrote it further down here. Oh, no, yeah, it's here. So the Elliott and New showed using Chern character that RC of C of X is bigger than or equal to, so let's see, I put here. Oh, sorry, the one other comment I forgot to make back here. So note RC of N of A, because the traces are taken to be normalized. So if you compute the rank with respect to the 2x2 matrices, it's half what you did with respect to just C of X. And so this gives you 1 over N RC of A. We'll put that up here so people can see. Okay. So that's not what I actually wanted to put yet. Sorry. So it's known. I would say the upper bound first. That RC of C of X is less than or equal to the following stuff: 1/2 of dimension of X minus 1 if the dimension of X is odd, and 1/2 dimension of X minus 1 if it's even. So this is really sort of algebraic topology related stuff. And some point set topology. So Elliott and New showed RC of C of X is bigger than or equal to something close to these. but with, and I'll say more about this in a little bit, rational cohomological dimension in place of dimension of X. And they agree if X is, say, a finite complex, but not in general. X reasonably nice, not in general. And the method uses rational cohomology, check rational check cohomology, and Chern character. And I'll try to say something about this, how it fits together. So we now know now, I mean, if you were at Elon's talk, you'll remember that there was a mean cohomological dependence dimension, which was defined using rational cohomology. So this is a sort of lower bound that we got. And it was based on generalizing basically using the methods from here. And I'll describe how that worked. We don't know how to do the analog yet, but we now know a better theorem that RC of C of X, and this can surely be improved, is bigger than or equal to it's 1/2 of dimension of X minus 7. And this is the covering dimension. And this is something that I did in July in Münster. And it's not yet on the archive, but I still want to actually improve things. I mean, the minus, you can do a little somewhat better depending on whether a dimension is even or odd, and if it's and one of them whether either dimension or dimension minus 1 is divisible by 4 or not. Okay. So I'll tell you something about how this works. Not going to write down the proof or anything, but I want to tell you something about how this works. But I should also say what the rational cohomological dimension is. In fact, maybe I won't actually write down the correct version, but roughly what I'll do. So the rational cohomological dimension of X is approximately the largest D such that there exists a closed subspace with check cohomology dimension D of X of not X, Y, not 0. This is not exactly correct. And if you try to make this definition of dimension, then it's some space with the same dimension, it gives different answers by 1. But at least this is always true if you take D to be 1 less than the dimension of X for a finite complex or whatever. Okay, that's the wrong page. This is what I want. Okay, so let E be a vector bundle over Y. It has Chern classes Cj of E in check cohomology. So again, for nice spaces, this is the same as singular cohomology. So if you don't like check cohomology, think of singular. Czech, I guess, was, I don't think the C with a accent over it is a letter in the Czech language, so I think he must have been Polish or something. He is Czech, okay? That is Czech, okay. Oh, I see, okay. This gives is in Z, and they have the properties. C0 of E, and I forgot, made one mistake here. I forgot the index, and it should be 2J there because we're looking at complex bundles. It's only even cohomology that's related. Z, sorry. C0 of E is 1. Cj of E is 0 if J is bigger than the rank of E. So here I'm implicitly assuming, so if Y is connected. And this is, all of this is if Y is connected. I won't go into the situation if not. What's 1? Well, if Y, oops, this is supposed to be Y, sorry. So I took a vector bundle over Y. If Y is connected, then H0 of Y is just a copy of Z with a standard generator. And what more do I want? If I take C of E equals the sum from 0 to infinity of Cj of E, this is now in the even Czech cohomology. Or the total Chern class. As C of E direct sum F equals C of E times C of F. This is the ring structure in cohomology. Okay, so let's check here. Oh, I should say this is also natural. Right, you do pullbacks of bundles with pullbacks of the cohomology class. And I will make one comment, then I'll stop for a break. One gets an isomorphism K0 of X, well, it's Y here, sorry. Y tensored with Q, even Czech cohomology of Y with coefficients in Q. And one has to pass from Z to Q to untangle this. To get an additive map. Where you would untangle the fact there's a product there. Okay, so I've been going for what, somewhere close to 50 minutes, and I will stop for a break. Questions?
So this result, maybe you said that there's a global assumption on your space Y, but is this true for what CW complexes or spaces on the top?
Oh, yeah, no, this part is true for arbitrary compact, I don't even need metric, but certainly compact metric Y.
Uh-huh. Okay.
So the appropriate versions of these things are true for arbitrary, at least compact metric spaces Y. Here, the zero check homology may be bigger than Z, but there's still a canonical class which corresponds to 1 and which is the identity in the ring multiplication. And so reinterpreting that, and then here, the rank of E should be the largest dimension of any fiber. You can, of course, split the space into different parts depending on what the fiber dimension is. And then on the separate pieces of it, you'll get some better bounds in the check homology of those subspaces. But yeah, I didn't really want to go into that, so I suppressed it. But yes, if you do things right, then that's what you have to do.
Chris, regarding to the statement about the lower one for the radius of comparison of C of X that you mentioned. So with this lower one, you should disregard the space or topological space when the covering dimension is less than or equal.
Yeah,
to
I should.
7.
Yes, I should have. Where is it? Is it still there? Yeah, yes, that's a mistake. I should have said the upper bounds, the correct upper bounds. Are the maximum of 0 and what I wrote. For the lower bounds, if you got a negative lower bound, then of course it doesn't tell you anything. So this is a correction here for RC of C of X. Because it tells you that C of X is not classifiable. Of course, C of X is also not simple. So.
Okay, any other questions or comments? Okay, if not, let's thank Chris, and we will be back in 50 minutes. Okay, we will resume the second part of Chris' talk. Okay, Chris, go ahead. And
Okay, so I want to give an example of these ideas in action. So I'm going to let E0 is the tautological bundle over CP1, which is really just S2. So what is it? I mean, this is all lines in the complex plane, and the fiber over a line regarded as a plane in the plane is that line regarded as a vector space. And then the total Chern class of E0 turns out to be 1 plus eta for a suitable generator eta of, since the space is good, I can just use singular cohomology, H2 of S2, and I'm going to omit the Z coefficients in the notation. And now I take X, let's say Y is going to be the product from, well, I should just take S2 to the N. And I have projections pi j y to S2. And then we can form the direct sum from j equals 1 to n of pi j star of E0. All right, so this is a rank 1 thing, so this has rank n. And the cohomology, so H star of y is the polynomial ring mu1 mu n mod the relation that all these things have square 0. And what is mu j? Let's see, I should probably leave this up. Mu j is just the pullback of that generating class in the case n equals 1. Mu j is pi j upper star of eta. And then one gets the Chern class of pi j star of E0. I gave this thing a name, didn't I? Call this E. Will come out to be 1 plus mu j. And the Chern class of E is going to be now the product from j equals 1 to n of 1 plus mu j. And now suppose that I want to embed E in a trivial bundle. Okay, so then, so the trivial bundle has total Chern class 1. So C of E, C of F is C of E direct sum F equals 1. Therefore, C of F is C of E inverse. And using this relation, where was it? It's there. This turns out to be the product j equals 1 to n of 1 minus mu j. And for j equals n, so in degree n, degree 2n, sorry, you get the non-zero term. Mu1, mu2, these are really cup products. We'll write like that, mu n. Therefore, the rank of F is bigger than or equal to n. And so if you estimate this, that where it was, if you use this to estimate the radius of comparison, it's not on that page. Okay, I wrote it down somewhere. I've lost where it is in my notes. Sorry. Yeah. So this gives. So then if this y is included in x, then get RC. I hope I actually did this right when I was doing it. C of x is bigger than or equal to n minus 1. I'm not sure I actually got exactly the right thing here, but at least something like that. Okay, so now, because it's heuristically, in fact, more than just heuristic related, I want to say a little bit of how to make a direct limit C-star algebra with large radius of comparison. So I want to. So this construction is basically due to Andrew Tom's, but I've modified it a little bit for present purposes. So I'll take AN is now going to be C of, no, I want M R of N of C of S2 R of N with R of say 1 equals R of 0, dividing R of 1, dividing, etc. And the maps, well, so A1 to A0 is F maps to the diagonal. So F is, sorry, A0 to A1. This is C of Sn, S2 rather. This is a matrices. Diagonal of F, I'll use the same letter for the projections. F composed with pi 1, F composed with pi R of 1. And then you do something similar with the rest of them. Right, you have projections, right? The R of 2 power is the product of R of 2 over R of 1 copies of the R of 1 power. And so this gives you what goes here. And you get also that A0 to AN has essentially the same form. But go up to R of N. Okay, so I guess I will put that up and not use that board. Back over here. Okay, now I'm going to ignore the fact in the notation I'm supposed to do these things in matrices. So I'll let P0 correspond to the projection over C of S2 correspond to E0. And then I look at, I should give this map a name. Okay, so we'll have phi NM should map AM to AN. And then we get phi N0. P0 is, so what is it? Well, right, it's P0 composed with these various projection functions. And what you end up with, so this corresponds to the vector bundle, the direct sum from J equals 1 to R of N of pi J upper star pullback of E0. And we saw if F is trivial, F rank less than R of N. So, sorry, less than rank of let's say E. Less than rank of E. Then, oh, sorry, plus R of N minus 1. Then E does not embed an F. But because I've taken matrix algebras, I have to divide by the matrix size. Stage N, I have to divide by R of N. Okay, so what we're now, I mean, what you really have to do is look at something in the direct limit and get back, and I won't do that. But you end up with RC of the direct limit of being roughly 1. This is not simple, but if you put in a very small number of point evaluations, you can make it simple and not reduce the radius of comparison very much. with RC nearly this large. Tom's wanted the K theory to be trivial, so he used the three-dimensional cubed instead of S2. But S2 embeds in it. And if you want larger values, then you'd better use S2n or something like that. Or maybe take a product, a bunch of copies already at the 0 level of S2.
So Chris, you can do this procedure for any real number and then come up with AH algebra or even simple AH algebra such that RC of that CS algebra is equal to this real number.
Yes. Did Andrew Tom? So you have to be a little bit careful. Andrew Tom said a somewhat more roundabout argument. The reason is that he used 0, 1 cubed and then products of copies of that. And so the actual value of the radius of comparison is bigger, which you will see, but you only see this by starting at some place above level 0. And he didn't do that. So he just got a lower bound. Then he had a separate argument to say, okay, if you get any non-zero value, you can get all real values. If you do this, then if you do it correctly, and I was very sketchy here, then you can actually compute exactly what the radius of comparison is.
I think that in my thesis I did it. I mean, for given any real number, then we can construct a simple AH algebra such that RC of A is equal to R.
Yeah, yes, you can do this explicitly, but I mean the fact that that exists is already in Andrew Tom's paper. But he did it in a more roundabout way. Okay. So now I want to switch to what mean dimension is. Before I do that, questions? Have people seen this before, by the way? Yeah.
I think I did Tom's thought about his sort of construction years ago in Copenhagen.
Yes, okay. Okay, so just some reminders of dimension. So X is now compact metric. U will be an open cover, a finite open cover. Its order is the least n such that the intersection of n plus 1 distinct sets is empty. This is normalized so that if you take a cover by disjoint sets, then the order is 0 and corresponds to be as the space in which you do this being 0 dimensional. V refines you if every set in V is contained in a set of U. Elon probably wrote this up or had this on his slides. Then D of U is the least order of some refinement. And the dimension of U, of X rather, is the sup over finite covers U of D of U. And there are pictures one can draw, which I've done in some talks, but I said enough about these other things that I don't have time to draw the pictures. I'll say just one thing. When you want to prove that R2 has dimension 2 rather than 3, you do not want to cover it by neighborhoods of squares. You want to cover it by neighborhoods of hexagons to get the right order. Yes, of more than. Yes, thanks. Yeah, if they're disjoint, then the intersection of one set won't be empty, but the intersection of two of them will be. Yes. Thank you. I'll need the least common refinement written like this. And what is it? Said all the intersections. And now I'll take H, X to X, homeomorphism, need not be minimal. And I will define, I'll take the mean dimension of H to be equal to the sup over U. I'll write down the expression and say something about it afterwards. I'll take the capital D of not of U, but of U join H of U join H to the n minus 1 of U. And I'll divide by n. And I forgot something in here. The limit as n goes to infinity. Let's check the limit exists. So with each iteration of H, starting with the open cover U, I see in principle more of the space. How much more do I see? Well, in the limit, I see this much more. And in fact, this is designed so that the shift on k to the z, let me actually not use letter k, let me call it p, for a finite complex p, has mean dimension equal to the dimension of P. Right, so heuristically, suppose U0 is a cover of P, which gives you the dimension of P. And then we look at, so let pi j be the amount from P to the Z to P. And I'll look at pi j, pi 0 star of U0. I'll take that to be U. So this is done set-wise. I take the inverse images of all the sets. And this is the, so this cover depends on only one coordinate. But if I take the join, if I take u join h to the minus n plus 1 or n minus 1 I have here, this depends on n coordinates and sees dimension of p to the n, which is n times the dimension of p. But I divided by n. So this is the right normalization. Okay, I'm cheating here because the original u can depend on more than one coordinate, but it can only depend on finitely many coordinates by the definition of the product topology. Okay, the shift is not minimal. The only known construction of minimal homeomorphisms of large mean dimension is certain sorts of subshifts, which Elon said something about, and which I'll briefly mention again. But the conjecture is that the radius of comparison of C star of ZXH is half of the mean dimension of X, of H rather, for minimal H. And there's a generalization to countable minimal groups. Yes, yes. And so we know, so the less than or equal is no. No. I think it was just new, maybe it was new and somebody else. But not much is known the other direction. As far as we could tell until recently, all that was known was RC of cross product bigger than 0 for examples of Gilles and Kerr. Okay, so there are examples of H with mean dimension of H bigger than 0 of minimal H are subshifts. So I restrict the shift to some closed invariant subspace with a density parameter rho and a set J contained in Z with density rho such that, and a point Z0 in P such that the product over n in Z of, well, let me say, Pn. And here, Pn is Z0 if n is not in J and is equal to P if n is in J. This thing is contained in X.
What's P, sorry?
P is this original space, right? I'm taking, where is my shift? Where was my shift? Up here. Here.
What do you mean by density parameter?
So this is, so basically it means this, and the point here is that the limit as n goes to infinity of the cardinality of J intersect -1 minus n divided by 2n plus 1, which is the cardinality of this interval, is rho. So if I take the even integers, I have density 1/2. This is some attempt at a measure on subsets of Z. It's not countably additive for obvious reasons. And not everything is measurable. The sets J which appear are not arithmetic progressions, because if they were, you would not get a minimal homeomorphism. But you still have a density. All right, in the construction, you get a thing like this, and there isn't anything with larger density. And of course, since it's invariant, then all the translates of this also have to be contained in X. All right, so this is something that looks rather strange. I mean, this is a right. It's a misleadingly simple example of a subset of X. Okay. So now we have H from X to X. And I have D real. And I will say the mean chronological independence dimension of H with coefficients Q, which I will suppress, is bigger than or equal to D if the following somewhat complicated thing happens, but it's some chromological version of this in which these joins are replaced by cup products, but I have to omit some of them rather than being able to average them out, the ones which don't do any good here, which leads to trouble. So for epsilon bigger than 0, there exists a closed y in X, and it will be pi 0 inverse of P intersect X in the shift situation. A finite open cover U finite open cover of Y by subsets of X. And so with, oh, and there's a K here. K is an even integer. That's what, and so now here's where K comes in. with, well, okay, well, see in a moment with, okay, so I take I regard U by intersecting with Y as an open cover there. I take this capital D of it. And that's what I mean by D sub Y is in K and K plus 1. K plus 2 allows interference of different values of different Chern classes. That has to be avoided for technical reasons. And eta in cohomology of degree K of Y and U and Q. So check cohomology is made out of open covers. And so this means we use the cover. Well, it's really U intersects Y in the definition of the check cycle. Such that for all delta bigger than 0, there exists a non-empty finite subset F in Z. It will be a long interval. At least in the examples. In the general minimal case, you have to use various kinds of Fulner sets, such that F is minus n to n intersect Z a delta invariant. And so this is if minus n to n, then this means just that, what did I get? I ended up with, what was it? 2n over capital N is less than delta. That's, I won't write down the definition of this, but that's what it is in the cases of interest. And F0 subset of F such that the following things happen. One, and so I will take the cut product over J in F0 of Hj upper star of eta. This is not 0. This is in. Now, what is this? This is in the check cohomology. Now it's 2k times, no, it's k is already even. I don't need the 2, but k times the cardinality of F0 of now the intersection over J in F0 of H minus J of Y with coefficients in Q. So I know it was something smaller. And 2 is K cardinality of F0 divided by the cardinality of F is bigger than D minus epsilon. So F0 is supposed to be large. And having the K there, make sure I get the dimension rather than dimension divided by K. Is a kind of normalization. Okay, so I said in the known examples, I said what these things are. And so in the subshifts, the known subshifts, then this thing here, this is, what did I call that thing? is P. Oh, sorry. First of all, F0 is F intersect J, where J is that set over there. And this then is now, this is the intersection. Well, let's see. It's the inverse image of P to the power F0 under the corresponding projection. Okay. So what happens in known examples? Is if K or K plus 1 is the largest, is the degree, the highest degree of non-zero rational cohomology of P, then the MCID K of H is bigger than or equal to K times rho. I want a 2 in here. Let's see. No, I don't want 2 because K is already even. So imagine that P was a sphere, an even sphere. Okay, then you're getting rho, which is the density, times the dimension of P. Now the theorem is that RC of the cross product is bigger than or equal to, and here's what we actually got. Now you really want bigger than or equal to about half of this, and K over 2. K is bigger than right. This thing is always, density is less than or equal to 1. And so this the biggest thing you can get here is K. And so in the shifts, with density rho, one gets, and let's see, I can go here. RC subshifts. Sorry. RC of the cross product is bigger than or equal to, what was the formula we got? Half mean dimension of H times 1 minus rho over rho minus 2. If rho is close to 1, this is nearly half of mean dimension of H minus 2. If rho is less than or equal to half, it's useless. There is a version using elementary symmetric polynomials. Instead of just products. Elementary symmetric polynomials in all coordinates in F. They have just products of coordinates in F0. The disadvantage is that so it needs y equals x. But using this, one gets if P is S to the 2L with L integer, then RC of C star of ZXH is bigger than or equal to a half mean dimension of H minus 1. This issue is gotten rid of, but at a price. That's right. So in definition 1, I'm going to say that I'm going to, instead of this business, I'm going to forget about F0. And I'm going to look at the largest, instead of, I'm going to replace cardinality of F0 over cardinality of F with the largest degree of an elementary symmetric polynomial, which does not vanish on these iterates for now J in F.
And also, I kind of got lost in the.
Yeah, it is somewhat confusing.
So there exists an eta in.
Yes.
Okay, there exists one.
That's right. And you can choose a different one for different, although we don't do that, but.
And so the I is independent, right? The MCIP.
Yes,
So and this is some sort of independence.
that's right. Product being non-zero is interpreted as independence.
Okay.
But you see, this is based on a very crude measure of independence, namely you take certain of the iterates and you want the product to be non-zero. The elementary symmetric polynomial version uses a less crude measure of independence, namely I use all of them. And it gives better results, but unfortunately it turns out to be technically unworkable, at least so far, unless y is actually equal to x. The trouble is that with this, you need the intersection of all the translates of y, or of whatever it is. And if you use a proper subset, by minimality, that intersection is empty. And then you'll get anything. That's right. So yeah, minimality is not assumed anywhere. In particular, it applies to the cross products of non-minimal homeomorphisms. And like I say, it also works for an arbitrary countable amenable group. Whereas for the upper bounds, the best results are something somewhat beyond z to the d. Okay, so I'll say very briefly, so very rough, yeah. You prove the upper bound on mean dimension, the right one, when the action is free and minimal, and the group is, I forget exactly what his conditions were. Might have been elementary abelian, but probably more restrictive than that. But certainly includes z to the d for any d, any finite d. But it's still rather far from arbitrary countable minimal groups. This one works for any countable minimal group. Okay, so I'm essentially out of time, so let me just say sort of one word about how this is related. All right, so I take, I'm really looking at, and let me suppress taking matrix algebras. Well, okay, let me look at projection over C of X, C of Y. So it's positive element over C of X. So in matrices. And if you're sub-equivalent in the cross product to a trivial projection, then one can cut down by a large finite set, Filner set, in Z to something which is a subalgebra of something like M. Well, if I use this stuff over there, Mn plus little n, 2 little n of C of X, in which let's say positive element A goes to diagonal matrix. Okay, I'll use the top part of this board. Again, so assuming that my set F over there is actually an interval, the structure will look familiar. A composed with h to the minus n minus little n. A composed with h to the minus n plus 1. A composed with h to the n plus little n. So this is like in the examples in the direct limit construction. So the sorts of things which are used there also apply here. And of course, there's now here is one significant technical thing I've suppressed entirely, which is how you do this cut down. And you notice that if you start with, so if F is Z intersect minus n to n. Okay, and I will stop there.
Any question or comment?
Yes.
Basic question, but isn't there exists like a C-star algebras with the radius of comparison?
Yes. if I repeat the Andrew Tom's construction, or rather the version that I gave there, and if I use the Hilbert cube instead of S2, then you'll get one with infinite radius of comparison. Again, you have to put in point evaluations, but yes, you can make it simple.
These things somehow is far possible from being classifiable in some sense. Or is that a bad way
Well,
to look at it?
in some, at least vague sense, yes. At least among simple nuclear separable unital things. Whether that's a heuristically useful sense or not, I don't know. There are things known which are true, showed up in the work of Hannes Thiel with some co-authors, maybe Bosa, maybe Pereira, I don't remember. In which having finite radius of comparison tells you something. But not related to anything that's here.
Are there known examples of C-star algebras who have same Elliott invariant and the same radius of comparison and are nevertheless non-isomorphic?
You can probably make the K-theory agree, but you have trouble with trying to make the trace spaces agree. So you should be able to do this. Where should I write?
Is it reasonable to just throw in radius of comparison to the Elliott invariant and hope?
No, but not based on this stuff. And the reason that it's no is that the example in an earlier paper with Hirschberg, I think the title is internal asymmetry or something like this. We find, I mean, this isn't what the original interpretation was, nor what the example was made for, but this came out. It's a simple AH algebra in which the radius of comparison is somehow different in different parts of the algebra. Meaning that just radius of comparison as a number is surely not expected to be a useful invariant for classification. Should I go back to the other question? The one about the same Elliott invariant and yeah. So here I think is what happens. This is not checked. Take P to be a cube. So then take the subshift X, you start is X0 is the intersection from n equals 0 to infinity of Xn, decreasing intersection of invariant subsets. And so for the first one, X0 is P to the Z. X1, well, X1, let me say Z1 is the set of, so I fix Z0 in P is the set of X, which is some sequence in X0, such that the P coordinate xk is equal to Z0 when K is in probably R1Z. X1 is the union of the translates of Z1. Z2 is the set of X in X1. Xk equals Z0 when K is in R2Z with R, so R1 is large, R2 is much bigger than R1, and it should be somehow and not and relatively prime. Okay, I'm not sure this is what I remember of the construction. I've not gone back to check. But if this is right, then probably X is contractible. So the principal ecological sequence gives K0 of X to K0 of X to this is identity minus H upper star, or maybe H inverse upper star, K0 of C star of ZXH, K1 of X to K1 of X to K1 of C star of ZXH. What this is missing there? I saw a piece of colored chalk, because here we go. This is 0. This is 0. This is 0. So here we got Z, and here we got Z. And the order is the usual order. And the cost of 1 maps to 1. Okay, so it's independent of T. So the K-theoretic part of the L invariant is independent of T. And with reasonably large density parameter, if I pick T1 much bigger than T2, then I can prove the radii comparison are different. But I don't know what the tracial state spaces are. They have to be large because otherwise the mean dimension can't be non-zero. It's possible that the tracial space is always sort of maximal in some sense out of all possibilities. But the Poulsen simplex has the wrong universal property. That's right. The Poulsen simplex has everything as faces, and what you want is everything as quotients. At least probably what you want. Does anybody know if there is a simplex which is universal in that sense?
Yes, no.
Simplex that map onto every other.
That's correct, yes. And in some suitable way. I mean, I want to consider. Now, again, I'm not, even if I've got such a thing, I'm not sure if it works. Because what it depends is on is finding other things which are factor systems. Right? There are no subsystems because the homeomorphism is minimal. I have a factor system of map from X to some space Z. I have C of Z to C of X. Cross product by Z to cross product by X. Traces on X to traces on the cross product by X to traces on the cross product by Z. So that means if I can show that there are lots of factor systems, then there are lots of other simplexes with maps from the trace space of this cross product. Now, even if you've got such a simplex that which is universal, it's far from clear that the rest of all this actually works. So that may indeed be a mess. And that maybe the whole idea is wrong. Okay, if somebody knows how to construct suppose you're given an arbitrary simplex, can you construct a classifiable C-star algebra with that K theory and the given simplex as the tracial state space? If you can do that, then you'll also have an example. And never mind what without actually having to compute what the tracial state space of this thing is.
K0 is that, oh, K1 is also that, right?
That's right, yes.
I see.
Right, that's a zero map. This is, I should have put that in. Because these are the case because X is contractible.
Sure.
Sorry, I forgot to put that in. And I should have put it in color.
What was the question you posed?
Can you find two minimal homeomorphisms whose cross products have the same Elliott invariant but are not isomorphic? Presumably because they have different radius of comparison.
Right, but the one question you just asked about finding.
Oh, okay. So method one. So to deal with let's see, where did I write last? So method one. Well, okay, I'll put method one, say that's the one which I was just asking about. And I'll put the other method afterwards. We don't know tracial state space of C star. Let me call this thing, call the homeomorphism. H T. T is up there. We don't know the tracial state space of the cross product. XT, HT. But, so suppose given any simplex, what's a good name? Delta. One can find a minimal homeomorphism H of a let's say K of a space Y, such that the Elliott invariant has K1 is Z, K0 is Z with usual order, generated by class of identity, and the trace space is isomorphic to delta. Okay, given this stuff, there's only one possible pairing between traces and Kaiser. Then do this with delta equal HT. Oh, and so, sorry, this and I don't need to find dimensional and yeah. Yes, and mean dimension okay is 0. So the cross product is classifiable. Yes, forgot that part. Thank you. With T chosen. So you can prove that mean dimension of HT is bigger than 0. Method 2. Try to show that possibly if all the other parameters in the construction are the same, traditional state space of the cross product is independent of T.
If we could fix, if we could improve what kind of simplicity we can get, then that would.
With this, the K theory.
The K theory is, that's what we got. Right? It seems like we should be able to get more general simplicity.
Well, they're given as inverse limits of this. Well, okay, the particular version I saw this took an inverse limit in which everything in the system was the measures on the interval 0, 1. But I'm sure you can do it in other ways too. Yes, this is Thompson's construction of AI algebras, simple AI algebras with arbitrary trace simplex.
But it's based on this result and result. I seem to remember it kind of takes the limit of simplices and sort of factors it through the input.
I don't remember exactly how that was done.
More generality, not just cross products, you have a tracial complex that's has only finitely many points.
Yes.
Also needs
Even if there are even if there's countably many extreme points. Basically, what happens in this case is you can prove something called the small boundary property. And for Z, the small boundary property, I think is known to be equivalent to mean dimension 0. Right? For Z of the D, this is open, but yeah. So if you want to use method 2, then presumably this would work. If you, the most obvious way to try to prove something like this is to show that the tracial state space is somehow as large, is a maximal simplex in some sense, because XT has lots of factor systems. Now that may not be true. If it has only countably many extreme points, then yes. Only countably many extreme points, and the answer is yes.
There's no possibility of finding a non-classifiable
Oh, not by this method. Yeah, so what I'm saying about countably many extreme points, this is specifically for cross products by minimal homeomorphisms. Oh, no, okay, sorry, I misunderstood. So no, I don't know about the more general statement. I mean, no, there are no I think there are no non-classifiable things with unique tracial state. I think that's true of one of Jesper Dillison's examples. But I'd have to check.
Any other question? If not, let's thank Chris for the great talk.
Okay, thank you.
And thank all of you for coming, and a special thanks to Karen for managing the camera. Thanks a lot.